I have here Dr. Eroglu and Professor Ruta, and the title of the presentation is Non-Trivial Fundamental Path Band Buckling of Damaged Parabolic Arches. Well, the presenter is Dr. Eroglu, of course.
Yeah, can you hear me now?
Yes, yes, we hear you very well.
Okay, thank you. So I will start right away. Well, by the way, I must say that it is quite a nice organization to be a part of, so thank you for having me, by the way, I must say that. All right, let me go to full screen if I can, and maybe I arrange a laser pointer. Okay. We basically deal with stability of arches with concentrated damages, which may be transverse cracks for continuous beams or rods, you may say, or a failure of connection members in larger structures. I will introduce the arch model we used very briefly and how we modeled the damage, and then provide a simple numerical example. I will talk on it. We assume the arch is one-dimensional continuum with parabolic axis. These are basically the Eulerian description of kinematics and balance. We assume the arch is, of course, it is flexible, and in addition to that, it is extensible and shearable according to Mashenko model. Those were the field equations in finite form. We provide a linearization of those finite form equations about the reference configuration, which is free of any stress. And this linearization by perturbation approach provides the very well-known linear differential equation system of curved rods, obviously. We will use it to determine the fundamental path. We then perform another linearization, but this time about a prestressed and deformed configuration, which is basically a generic point on the fundamental path. By the way, the subscript F refers to fundamental path, but of course these are linearized approximations of the field functions of the fundamental path, I must say. We can show that under suitable assumptions, we can recover very well-known equations. For example, if you neglect the deformations of fundamental path, and if the curvature is equal to 0, you will end up with Euler-Coleman buckling equations. And if you assume K is equal to 1 over R and it is constant, then you'll end up with Mariotte equations for circular arches. These are the non-dimensional quantities, but to be honest, only when commenting on the results, these two will be of importance. The parameter alpha defines the initial configuration or initial geometry of the parabolic arch, and lambda here is a measure of its slenderness. The resulting equation system is of variable coefficient. It is homogeneous for bifurcated path, and it is non-homogeneous for the fundamental path. The solution to both are known in terms of a matrix called fundamental matrix or transfer matrix or matricant, whatever you may want to call it. It can be written by means of the matrix capital Y, let us say. For fundamental path Y of F, we can determine this fundamental matrix exactly, but for bifurcated path, we make use of some approximate solution technique which uses Peano's series expansion, and this procedure leads to a modified version of Volterra's multiplicative integral. To model damages, we use spring analogy. We assume the crack is open all the times, which can be debated, of course. We use spring analogy to examine the effects of damages on global behavior. With this model, the interactions, as you may see in here, the interactions are equal to each other at crack section, of course, after suitable projection, as you may see in here. But there will be a jump in deflection components. There will be, say, a relative strain, you may say, a relative deflection, you may say. And this relative motion is quantified by the compliance matrix and interactions at the cross section. And this compliance matrix is derived by means of the energy release rate, a concept of linear elastic fraction mechanics and Castigliano's first theorem. each term in this compliance matrix refers to certain mode of relative motion. Of course, this is a compliance matrix, and you may see some set of springs here. So basically, the stiffnesses of these springs will be quantified by the inverse of this matrix. But then again, it is easier to somehow show the relative motion and which component is responsible for those relative motions. I will very briefly highlight. The tricky part is off-diagonal terms. Here, CNM, C of NM, describes the axial displacement due to bending couple, and CMN provides the relative rotation due to axial force, and we make use of a parameter, a non-material parameter P, to describe the crack location on this section. When P is equal to 1, the crack is on top, we say, and when P is equal to -1, the crack is on the bottom of the section. Therefore, positive axial force will lead to different rotations. This is the numerical example we consider. We consider parabolic arch with fixed ends under a uniform line load of magnitude Q. The geometry varies from a really shallow one to a moderately shallow one, and we assume that the crack is located at xc is equal to 0.25. By the way, this is the origin, and this is equal to x is equal to 1. Of course, the non-dimensional version of it. We assume that crack might be on xc is equal to 0.25 or equal to 0.5. We always assume that lambda is equal to 80. This is relative crack depth. We assume that the arch has rectangular cross-section, and the crack is the depth of the crack is half of the height of the cross-section.
The time is over, Urgukan.
Okay, the conclusions.
Very well. Thank you so much.
Well, these are the interactions of fundamental path. We see the thrust follows the bending couple. When P is equal to 1, it increases its magnitude, and when P is equal to -1, it decreases its magnitude since M is negative. A similar pattern is observed when xc is 0.5. But here we see when P is equal to 1, the thrust is almost unchanged because the bending couple is practically 0 there. These are the critical loads, critical load ratios, critical load of cracked arch to that of intact one. We see that higher thrust leads to a lower buckling load, but we see something in contrast in here. This is one of the last slides of mine. This is the reason. The incremental bending couple and axial force admit opposite signs for the incremental behavior. When P is equal to 1, the axial force decreases the relative rotation at crack section, providing a stiffening, increases the buckling load therefore. When P is equal to -1, the incremental axis load further bends the chunks, and this increases the local compliance and leads to bifurcation at an earlier stage. These are some key points. Of course, there's a lot more to comment, but time is quite limited, it seems. So on behalf of Giuseppe Ruta of Sapienza Università di Roma, Ekrem Tüfekçi of Istanbul Technical University, I, Uğur Eroglu of İzmir Ekonomi Üniversitesi, thank you for your attention.
Thank you so much, Urgukan, and please give my greetings to Giuseppe.
Sure.
Very nice presentation. Are there any questions about this topic, this paper? No question. I have a quick question. I want to ask you if it's possible to consider also a geometrical imperfection of the arch together with the crack presence. And the second one that is connected, if it's possible to consider not only one discontinuity, but for example, a crack pattern on the arch.
Yes, I mean, let me start with your last question. In fact, it is of course possible, and we provide an iterative procedure to deal with multiple cracks, and I had provided some references to it. Yes, I'm not sure if you can see it, and in this article you may find an iterative procedure to deal with multiple cracks, obviously. As per imperfection, I think it will have more impact when the arch is shallow, because then there might be the possibility of symmetric loss of instability and skew symmetric loss of instability. And at that time, I mean, when the arch is shallow enough, then there might be the impact of imperfection. I mean, we haven't dealt with that, but when the arch is quite shallow, then the imperfection will play a greater role, obviously.
Thank you so much. Thank you so much.
You're welcome.
Question? Okay. Thank you again, Jurgu Khan, for your presentation and for your answers.